All right. Greetings from my basement. I'm not on campus today, so I thought I was going to give this a try. Smaller whiteboard, so hopefully we'll be able to make do. In this video, we're going to talk about nuclear fuel, right? So we went through all the processes, the geological occurrence, how uranium-bearing minerals are deposited, and then how we concentrate them and get this product called yellow cake, right? Different than the yellow cake that you get for your birthday. And at this point, if you guys remember, one of the big things that I was harping on earlier is that in the natural occurrence of uranium, the isotope that we're after in this case is uranium-235, and it's naturally present at about 0.7%, so really not very much of this naturally occurring uranium. And what we need to do is enrich that, or essentially change those percentages. And this is where we leave the realm of what I referred to earlier as safe uranium. Again, this is something you hear about on the news. We're talking about uranium enrichment at this point, right? So it's occasionally a news story, and we'll hopefully see why in a little bit. So again, the most important thing to remember going into this is the different isotope percentages. So initially, we have uranium-235, 0.7%, and essentially what we do at this point is we take that yellow cake uranium and we heat it up and convert it to a gas. So now we have a gas that is mostly uranium-238, which if you remember has some extra neutrons, is a little bit heavier, and a small percentage of uranium-235. And we put this into, I've kind of just drawn a conceptual model here. We'll look at we'll look at a diagram that kind of shows how this works in the real world, but this will just help us think about the process. So that uranium gas is essentially inserted or kind of run into the cylinder here, and it's spun around. So it's spun in this gas centrifuge. So a centrifuge is something that takes advantage of centripetal force. The same thing that you maybe have experienced on a merry-go-round, right? The idea that as you're spinning, you get forced to the outside. But if you think about that same force, and one of the fundamental laws of gravity is that things that are heavier are going to react to that force in a different way than things that are lighter. So as these gases are spinning, essentially what happens is the uranium-238 gets kind of pushed to the outside of this centrifuge, and the inside, kind of like the inner, almost like a core, if you could think about it that way, is the lighter elements. And in our case, that's uranium-235 that we're after. So I'm going to erase my arrows here and just, again, draw kind of a conceptual model about where these different gases would be in our centrifuge. So here again, to the outside, here to the outside you can see uranium-238. And then this kind of inner core, that's a much higher percentage, or that's where the essentially displacement has occurred, that we get enriched uranium-235. And if we were to want to collect that, we could, again, this isn't, these machines are much more complicated than this, but simplistically, we could essentially take a straw and stick it into the center of our centrifuge, and if we were extracting the gases just from this core, we're now pulling out uranium-235. We can take that gas, concentrate it into a liquid, dry that liquid out, and go back to our solid form. But now we have uranium that's been enriched. So one of the things that we're going to explore in a subsequent video is this notion of using uranium as a fuel, actually this kind of controlled decay reaction. But the thing that's important to keep in mind when we're using uranium as a fuel is uranium-238 decays naturally, uranium-235 decays naturally. This is spontaneous decay. Uranium-238 decays much more slowly than uranium-235. And uranium-235 also has this interesting characteristic that we can, under certain conditions, accelerate its decay. So if we want to take advantage of that accelerated decay and capture the heat generated by that radioactive decay, we're going to need 235. To use it as a fuel, there's kind of some minimum concentrations. Generally, it needs to be higher than about 3%, which I remember initially it was at 0.7%. So generally about 3% for a fuel. oftentimes is produced at about 5% for a fuel. So herein lies the problem, although you probably haven't really realized it yet, because we haven't talked about it in detail. So again, 3 to 5% for nuclear fuel, that would make you a viable nuclear power if you were a nation, right? If you were able to enrich uranium to this level, which isn't all that much, right? Not that hard to do. When you have a contraption like this gas centrifuge, there's nothing in this centrifuge that's preventing you from actually creating pure uranium-235. And again, something that we're going to explore in a later video, when we enrich to a high enough level, remember that I said under concentration it will actually kick off other reactions. Once we're at a really high rate of uranium-235, so above 85 or 90% uranium-235, at that point, the uranium will kick off decay reactions so efficiently and so quickly, it's actually what we would call weapons-grade uranium. So at these concentrations, that decay chain happens so quickly, it accelerates essentially out of control, and kablooey, we've got uncontrolled decay of uranium and essentially an atomic bomb or nuclear weapon. And again, this becomes one of the issues that if we have a facility that's running this sort of operation, enriching uranium to the level of fuel, there's not a lot preventing a state or an organization from actually enriching up to a much higher percentage. But we're going to come back to visit that idea. So that becomes one of the shadows or the kind of murky areas in nuclear power. When we're doing this gas concentration, as you can imagine, one centrifuge, and you're pulling out a little bit of uranium-235 out of the core, it takes a lot of gas to re-solidify and make a solid mass, right? Remember, generally things are smallest solid, larger as a liquid, and then even larger as a gas. So you can see in places where we have these uranium enrichment facilities, there's just banks and banks and banks of these gas centrifuges. I know we talked about the concept. You can see here, after we've seen these walls of them, this is essentially a diagram of how one of these things work. They're generally vertical, and you can see it's got, casing and all of those sorts of things. But it works exactly like what we're talking about. And they provide a great photo op, right? So anytime you see a news story about enriching uranium, there's a photo of some world leader in a room full of these gas centrifuges, right? Which again are pulling out concentrated uranium. And now, maybe when you reflect back on the news stories and these countries are saying, no, we're enriching to the point of having a nuclear fuel program, having a nuclear power program. And a lot of people are concerned because we might not be able to know if they're also enriching to weapons-grade uranium. Now we have buckets full of enriched uranium, and we need to do something with them. So at this point, there'll be a company, a nuclear supply company, and what they'll do is they'll take that enriched uranium and they'll actually encase it in small little ceramic cylinders, and that is a nuclear fuel cell. You can see there, we'll talk about some of the reasons why, but they're essentially safe to handle. The accelerated decay chain isn't happening. They're not as safe to handle as just raw ore because there's a higher percentage of uranium-235. But again, the goal here, these little black things are about 4% uranium-235, and that's the fundamental energy unit for nuclear power. We don't just put these things in a big pile. As we'll kind of examine when we start talking about reactor types, essentially what we do is we take a metal sleeve, if you were to imagine like a pretty thick straw, and stack a whole bunch of these little tiny fuel cells together, and that is what we would call a fuel rod. So this would be a diagram, like a cross-sectional diagram of a fuel rod. And again, there's different types of fuel rods for different types of reactors. We do have one dominant kind of reactor, but each individual fuel rod probably not much larger than the diameter of my expo pen here. And then those fuel rods, we essentially nest them together to make a fuel assembly. And this pattern is repeated, right? We have many different fuel assemblies, each containing a bunch of rods. And then within these rods, each having a bunch of these little fuel pellets. So that's essentially our power source. Because as we kind of look forward, we're going to take advantage of the heat created by this radioactive decay to ultimately create steam and spin the magnet, right? But this is our getting us to our fuel. So at this point, we've got our individual fuel cells in our individual fuel rods. Those rods bundled together as these kind of much larger packages of nuclear fuel, and then those themselves bundled together. And now we have our energy form. And at this point, we're going to have to start talking about, again, a little bit of chemistry, but not too much, of what then happens once we kick off that decay reaction. So we're not quite to that part yet, but that's one of the things that makes uranium-235 so special.